Hey there, my name is Bart Baasens, and in this session I want to talk about managing model risk. In case you're interested in further information about the topic, or in case you're interested in the slides, you can always contact me at the email address indicated below. I'm a professor at the Catholic University of Leuven, by the way, working on data science and analytics. And the topic of this session is managing model risk. It's based upon this book, which I co-authored together with an ex-PhD student of mine, Professor Seppe van den Broeke, who is a professor at Ghent University and also a part-time lecturer here with us at the Catholic University of Leuven in Belgium. For those of you that are interested, you can find the book on Amazon. In this session, I'm only going to briefly highlight some of the topics of the book. I obviously don't have the time to go through all of the topics, but I handpicked some of them of which I think are very interesting to be aware of as you're starting to productionize, deploy machine learning models and want to be aware of all the risks that come with this. So first of all, I would like to start by setting the stage, and the idea of the book was kind of initiated by a FICO report that was published in 2021. FICO stands for Fair Isaac Corporation. It's actually a credit scoring company which is based in California in the United States. And a long time ago, I had the honor to teach to some of the FICO people the wonderful world and concepts of credit scoring. And in 2021, they published a report in which some very interesting findings came out, like 65% of the companies cannot explain AI, artificial intelligence, machine learning, or analytics, model decisions, or how predictions are being made. That's a lot, given the fact that more than ever before, AI models, machine learning models, steer the strategic decisions of firms across the globe. 73% struggle to get support for prioritizing AI ethics. With recent developments such as large language models, but also developments in deep learning, AI ethics is more and more becoming a prominent issue in the sense that what are we allowed to do with AI? What kind of data can we use? What kind of techniques can we use? And how can the models be used? So there's lots of ethical aspects that come with productionizing or deploying AI or machine learning models. Only 20% of the companies that the FICO surveyed in their report actively monitor or backtest their models. A famous colleague professor of mine, who is now retired, David Hand, who used to work at Imperial College in London, once said that as soon as you put a scorecard into production, it is outdated. And actually, we can generalize this from a credit scoring context to any type of machine learning applications, because a machine learning or analytical model is always built using a snapshot, a sample of data, which means it is conditional on that very snapshot or sample of data. But obviously, as machine learning or analytical models are starting to get used, deployed, or put in production, the environment changes. The external environment changes, the company environment changes, but also customer behavior continuously changes. Think about fraudsters, for example, who continuously change their tactics in order to stay inconspicuous or unnoticed within the entire set of customers. So it's very important to put in place mechanisms that allow us to monitor or backtest analytical models. Analytical models are more and more also being subject to security concerns. The report mentions that 30% of organizations report an increase in adversarial and other model attacks. Now, one question is, how can you attack an analytical model? Later on, in this presentation, I'm going to discuss how model attacks can take place. We're going to talk about model outsmarting, about model backdooring, about denial of prediction attacks, all kinds of, about model exfiltration, all kinds of attacks that analytical models can be exposed to as they're being productionized or put in production. So, like every good book, we started first by trying to define model risk. And we define model risk as the risk of unexpected or expected loss resulting from the inadequate development or usage of analytical models across all business units and activities of the companies. So any type of business unit, be it the marketing, HR, production and logistics, finance, accounting, any of those units that is using analytical models to either target customers, to detect fraudulent transactions, to evaluate creditworthiness, etc., every of those units that is actually using those models is exposed to model risk, which can cause expected or unexpected financial loss. So the first important thing when you talk about model risk is qualify the model risk, identify the model risk before we can start looking at ways to deal with it. And actually, the idea of model risk was first initiated by George Box, which is very well known for the um, box plots, which are a very well-known mechanism to detect outliers in data. You still remember that a box plot kind of depicts the median, the first quartile, the third quartile, and then it has some edges connected to it, and points falling outside of these edges are then denoted as outliers. Well, in 1976, which is 1 year after I was born, George Box essentially stated all models are wrong, but some are useful. And that very nicely captures the core idea of model risk in the sense that as soon as you put an analytical model in production, as soon as it has been estimated, in fact, it is wrong. But if it's useful, if it allows me to detect fraudulent transactions or defaulters in a better way than a random model, then obviously that analytical model is starting to be useful because we can actually get some insights and performance from it in terms of discriminating the fraudsters from the non-fraudsters, the tuners from the non-tuners, the defaulters from the non-defaulters, etc. In our book right here, we kind of started from the CRISP-DM model. That was a model that was originally developed by SPSS and later on adopted by IBM. Stands for Cross-Industry Standard Process Model for Data Mining, so it still uses the old term of analytics, machine learning, which was initially data mining. And it looked at the entire cycle of building a data mining or analytics model, which typically starts with business understanding, like what is our business about? Are we talking about insurance fraud, car insurance fraud? Are we talking about customer churn? How do we define churn? Are we talking about credit scoring? Do we want to detect defaulters? How do we detect defaulters? So first of all, you start from some business understanding. That gives you some data understanding because then you will look at what is the data that could potentially be useful to differentiate the fraudsters from the non-fraudsters, the defaulters from the non-defaulters, the tuners from the non-tuners. You'll try to gather as much as possible data, internal or external, that relates to that, and then start preparing that. And in my course, I already extensively discussed how you can pre-process data by sampling it, by taking care of missing values, by detecting outliers and treating them, by doing some coarse classification or categorization, some weights of evidence encoding, etc. And that kind of jointly goes with the modeling. The modeling is when you're going to estimate a linear regression model, a logistic regression model, a decision tree, maybe a deep learning model like a convolutional neural network model in case you're working with imagery, etc. And then obviously all the models that are being estimated need to be evaluated, and we evaluate models by looking at various dimensions, like looking at statistical accuracy for linear regression. We're going to look at R-squared, mean squared error, mean absolute deviation. Case of classification models, well, for response modeling, we're going to look at lift curves. For credit risk models, we're going to look at area under the ROC curve, Gini coefficients, etc. And then once this all has been nicely approved, once we have an analytical model up and running, we can start deploying it. And you see that each of those steps of the CRISP-DM model could be affected by model risk, right? So in the chapters of our book, we will start upper right corner by discussing data risk, right? What are the risks of having bad data or data that's not predictive? How can we deal with that? So there's various topics that we discuss there. Then there will have like specification risk. Specification risk, we're going to look at, in the book, we look at incorrect target definition, uplift modeling, which is a special way of looking at a way to define your targets, improved loss function, multicollinearity, which I will also elaborate on in this talk, and buggy digital twins. During the development itself, in chapter 5, we also have development risk. And in the book, there's a plethora of topics that I discuss or we discuss that relates to development risk. But we're going to handpick some of them, like we're going to talk about the citizen data scientist, we're We're going to talk about data leakage, that is very important, about assumptions, model isolation, and open source versus commercial software. That's what we will talk about in this presentation. Validation risk. In the book we talk about test set torturing, incorrect cross-validation, which is also an important thing. In this presentation, I'm going to talk about unexpected signs, and we're going to talk about model auditing and also model benchmarking. Chapter 7 relates to the deployment, where analytical models may get exposed to operational risk. And here we're going to talk about, in this presentation, about data drift, output drift, and target drift, for example. But in the book, we also say a few more words about model overrides and model retirement. In Chapter 8, security risk, as I said, analytical models are being more and more exposed to security threats. So here we're going to talk about model outsmarting, model backdooring, model exfiltration, and denial of prediction attacks. And we conclude this session, and also the book obviously, by saying a few words about managerial risk. I'm going to say a few words in this presentation about transition risk, model governance, waste of analytics, and model ethics. But in the book we also talk about model anxiety, automated machine learning, and whether companies are ready to hire a chief model risk management officer, which obviously they are. Let's first talk about data risk and data bias. And I'm kind of a history buff, so I read a lot about history. I read a lot about World War I, about Napoleon, about World War II, and so on. So every now and then there's like an interesting example that I pick from some of the blogs that I follow, and it allows me to illustrate an analytical point very nicely. So we go to the Second World War, when Britain was bombing Germany, and so it sent out some of its bombers, and Great Britain had some very sophisticated bombers like the Lancaster bomber, which is a very nice plane, but also a Vickers bomber. And obviously some of these bombers, when they were bombing enemy territory, some of them got shot by air defense, but some of them made it back home safely. So for the bombers that made it home back safely, the question was, how should the damage that was inflicted upon these airplanes, how should that be taken care of? So imagine that a bomber returns back to its RAF, Royal Air Force, home base in Great Britain, in England, and you see all the damage that is being done to the plane, right? So, and the red dots represent the damage, right? The red dots represent where air defense gunshots where the airplane got hit by air defense gunshots. So obviously the question now is, where should we reinforce the plane? Where should we put extra armor to make sure that more planes successfully make it back home? Well, obviously, it speaks for itself that what makes it back home is a sample bias. These are the ones that survived. We don't have any sample of the ones that crashed. We don't have that data available because they crashed all over the place, maybe some in the channel, etc. So you only have a sample, a biased sample. And actually, when you think a bit further about that, the ones that made it back home, well, actually, the ones that had gunshots right here and right here, corresponding to all the red dots, well, actually, that means that those are not very vulnerable places of the airplane in order to be shot, because they made it back home. So if we should put reinforcements or extra armor to protect the airplanes from enemy fire, then we should put extra armor on the places where there are no red dots, which are obviously the two engines, the cockpit, and some other places that we can consider. Because we can very easily deduce that if planes were shot in the undotted regions, in the regions where no red dots are present, then those planes probably have crashed, did not make it back home. So that's an example of how bias first can be detected, can be thought about, so you carefully think about bias, and then how you can use that bias in order to do what you want to do, which is, in this case, is protecting the airplanes and adding extra armor to them, so as to make sure that more planes make it safely back home. And actually, when you translate that to analytics, every sample you take is biased, because you always take a sample from a specific time period. So that means that it's conditional upon various types of characteristics. An analytical model that is built upon that sample will always work in a dynamic environment, in an environment that is continuously changing. Because every sample that you take, if you take a sample of uh, credit customers, if you take a sample of credit transactions, if you take a sample of credit card transactions, of car insurance claims, or if you take a transaction of your customers that you targeted with the marketing campaign, well, each sample is conditional on the state of the macroeconomy at that very moment. It is a well-known fact that customers behave very differently in macroeconomic upturns than they do in macroeconomic downturns, right? So whether you're in a macroeconomic downturn or upturn will undoubtedly affect credit risk behavior, possibly also fraud behavior and marketing behavior in general. So every sample is conditional on the macroeconomy, but also the firm strategy. What strategy was the firm adopting at that very moment? Was the firm adopting a very aggressive strategy towards its customers or not, marketing wise or not? Was it, if the sample was taken during period T1 and during T2 the firm did a merger or acquisition, then it speaks for itself that the population of the firm changes because of the merger and acquisition that was done. So that will also affect obviously the analytical model that was built on a sample that was taken at time point T1. Furthermore, we have the phenomenon of customer endogeneity. That means that customer behavior changes a lot. Like if you look at credit worthiness, for example, if you look back 30 or 40 years in time, then marital status turned out to be an important predictor for your credit worthiness. Nowadays, because of customer dynamics that have changed, because of socio-demographic evolutions and less people getting married, then obviously marital status is no longer a significant predictor when we're talking about credit risk. Actually, when you talk about credit risk, which is my area of expertise, where I do a lot of research on and where I also did my PhD on, we also have the reject inference problem, which is a very important source of data bias in any type of credit scoring model. And it means that if you look at a historical data set of obligors, of customers on which you're going to build your credit scoring models, then in fact, in that past sample, there has already been some filtering that has taken place. Because 20 or 30 years ago, if I went to a bank, if I didn't have any income, so I was unemployed, and I had lots of accumulated debt, then no way in the world I was going to get credit. Banks don't need credit. Banks don't need analytics to decide whether you're credit worthy, yes or not, if the signs are too obvious. So if it's too obvious that you're indeed unemployed, you don't have any income, you have lots of accumulated debt, then you're not going to get credit. You don't need analytics for that. So in the past, even before credit decisions were made using analytical models, also known as scorecards, the way decisions were made in the past was based upon expert knowledge, based upon a set of if-then-else rules, like if no income and if lots of accumulated debt, then no credit. And banks adopted many of those rules, which means that for those customers that complied with those rules, we don't have data because they were supposed to be bad payers. So the sample that we have in order to develop our credit scoring model has already been pre-filtered. It's the sample that is obtained after having applied those expert-based rules that banks were adopting in the past. That's the well-known reject inference problem. It's one of the most important problems banks face when building credit scoring models, and a lot of research has been done on this topic. It's the reject inference problem, right? And reject inference essentially is that we don't have any information about our past rejects. We can assume and hope that many of them would have turned out to be bad payers or defaulters. Otherwise, the old credit scoring policy was not a very good credit scoring policy. But obviously, there will always be gray customers, customers for which it was not black and white, whether they were good or bad, and for which a decision was made by a credit expert. Those are the ones that kind of are very important in terms of data bias, because those are the ones that maybe were rejected credit and may have turned out to be good payers. So reject inference in credit scoring is a type of data bias implying that we don't have any information upon our past rejects because of the old credit policies, often expert based, often based upon if-then rules which were used in the past. Another type of data risk is a lack of predictive power, right? Lack of predictive power implies that you have gathered a nice data set, but your prediction task is very hard. Analytics is not magic. It means not because you're gathering a data set and you're defining a target like default yes or no, fraud yes or no, or customer lifetime value. It's not because you gather a nicely pre-processed data set that you're going to get a meaningful analytical model out of it. All depends upon the predictive power of the variables, of the data elements. And sometimes this may be lacking. Sometimes the results you get with an analytical model can in fact be quite disappointing. And that's also a type of data risk that you can face as you start developing your analytical marketing models, as you start developing your fraud models or your default models. And there's a technique that can be used for that. The technique is called data augmentation. It's not like a one size fits all technique, but it could help you deal with the lack of predictive power. And a first thing is that if you have lack of predictive power with your internal data, the first thing you can do is you can go and look externally. You can go and look for external data from data poolers. There's lots of data poolers that are operating in the industry nowadays. Equifax, Experian, and TransUnion are some very popular examples in credit scoring. Dun and Bradstreet as well. You can also make use of Google. A very important application of Google, for example, is Google Trends. Google Trends allows you to see what are the trends in the search terms that people use when they issue their Google queries. So if you see that many people start looking for the term jobs, then it could be an indication that unemployment is on the rise. So Google Trends is an example of external data that could be useful in your internal models if you want to predict unemployment, for example. Same goes with Google Street View. I know of a study by Gebru et al., which was published in the Proceedings of the National Academy of Sciences (PNAS), Proceedings of the National Academy of Sciences, in which Google Street View pictures or images were analyzed to portray the economic makeup of certain types of geographical neighborhoods by just merely inspecting the types of cars that were driving there. So based upon the types of cars that were driving in certain types of neighborhoods, using Google Street View images, the authors managed to detect wealthy neighborhoods where expensive cars were driving from less wealthy neighborhoods, right? So Google Street View is another type of external data source that could come in handy. And then we have government agencies that publish all kinds of reports about how the economy is doing, about inflation, etc. That can also come in handy. You can also try and go after external data by using web scraping, right? So web scraping, we also published a book on web scraping, also with Seppe van den Broeke, where we published a book on web scraping for data science in Python. It's also available on Amazon in case you're interested. And what you're doing in web scraping is you're building a Python script that scrapes information from websites. The websites can be your competitors' websites in case you want to see whether your competitor recently launched a marketing action, yes or no, or could be any type of websites. You can scrape movie reviews from the Internet Movie Database. You can scrape any type of information from any website as long as it's available online, obviously. And that could be another source of information that could be useful. For example, I'm aware of one of my colleagues that scraped information about websites of small and medium-sized enterprises to help them boost the predictive power of their credit scoring model, to see whether the text that is present and the information that is being given on a website of a small and medium-sized enterprise, whether that tells you something about whether that firm is creditworthy, yes or not. Do note that these external data sources are all considered to be add-ons on top of existing data that you have. So the idea is always to add as much data as possible, start from your internal data, then add external data in order to tackle this issue of lack of predictive power. As I told you, I'm a history buff, so I'm also very honored to collaborate with the National Museum of the Royal Navy based in Portsmouth. There we got a data set of images that we had to classify. They were ship images, so it was about 5,000 images of ships, Royal Navy ships, somewhere between 1918 and 1990. And for each ship, we had like a description of the ship, and then we had to label the ship as being a cruiser, a frigate, a corvette, a sloop, a submarine, a mine layer, a minesweeper, etc. Obviously, for most of the ships, we only had a few images. It turned out that the prediction task was very hard because we wanted then to unleash a deep learning neural network, more specifically a convolutional neural network, to detect patterns of the ship and to help us label the ship as a destroyer, a cruiser, a battleship, a battle cruiser, a frigate, a submarine, etc. So what we did is we applied augmentation. We started from, let's say that to the upper left is our original image. Then we rotated the image a bit, right? We added a little bit more heavy clouds, which you can see right here. These are all the same images. This is all the same image, but manipulated in a certain way. So the ship you see on each of the images is identically the same. We just rotated a bit, added a little bit more clouds, etc. And what we're actually doing here is we're duplicating the same image in various ways so as to enrich the data and allow the deep learning neural network to detect more patterns from the few observations it has. That's another example of what we would refer to as data augmentation to help us tackle the lack of predictive power. Another one that we can do is feature engineering. The idea of feature engineering is to start from your transactional data, the data that's being stored in your transactional databases, and then think about crafting or creating very smart features that allow the analytical model to better perform its task. The idea is to transform the variables into features to boost the performance in terms of either predictive performance, sorry, like AUC R squared, or in terms of interpretability. That's what you want to do when you're creating smarter features. And throughout our research and the many benchmarking studies that we've conducted, and together with my co-researchers, I can tell you that we did quite a lot of benchmarking studies in credit scoring, but also in churn prediction and in fraud detection. We found that the best way to boost the performance of any machine learning model is by designing smart features. And designing smart features requires the close collaboration between the data scientist and the business expert. That is a very important aspect to be mentioned here. To show you the power of feature engineering, have a look at this plot. The dots represent customers. So every dot represents a customer. That could be me, that could be Anne-Sophie, that could be Victor, that could be Hannah, it could be Tim, could be Wouter, etc. X and Y indicate geographical coordinates on a map, so you can consider this picture to be a map. And the blue customers indicate the profitable customers, and the orange customers indicate the not or the unprofitable customers. And at the center of the plot, where X and Y equal 0, there's a supermarket that is located there. Obviously, it speaks for itself that the pattern that comes out is that the most profitable customers live in close proximity of the supermarket. So you can kind of see a very circular pattern there. Least profitable customers live further away from the supermarket. So if you want to perfectly separate the blues from the oranges, and you're using logistic regression can only draw a line, so it will not do very well. Maybe it just draws a horizontal line at y equals 0, or a vertical line at x equals 0, and it will have like a 50% performance, so it will not work very well. Decision trees will make splits that are orthogonal to the axis. So a decision tree will make a split like if x is less than 0, then first split, and then for each of the leaf nodes, if y is less than 0, or if y is less than 1, or if y is less than minus 1. So a decision tree makes splits that are perpendicular to the axis, so it would also not perform very well. This simple data set, only a few data points and 2 features or characteristics, actually is very complex to be modeled analytically. So you would have to resort to neural networks, maybe even XGBoost or deep learning neural networks to properly identify that circular pattern, unless you do some very clever feature engineering. And instead of Euclidean features in Euclidean space, you look at the polar coordinates. And a polar coordinate means that you represent every dot in the polar space by the size of the vector and the angle against the origin. R is the size of the vector where the dot is situated, and theta is the angle that the data point makes with the origin. So if we look at this dot right here, this blue dot, we would just look at the size of the vector that originates from the origin and the angle that it makes against the x-axis. And if we represent the same data set in polar coordinates, so if we engineer the features to polar coordinates, we now have two features, which are the polar coordinates. R is the size of the vector and theta the angle. Then we can do a perfect linear separation, and we can do a logistic regression. So if we do a logistic regression but on the polar coordinates, then, or if we do a decision tree, it will be a one-level decision tree. The decision tree will say if R is less than 2, then the customers are profitable. If R is bigger than 2, then the customers are unprofitable. It's a one-level decision tree which we obtained after having carefully engineered the features. Instead of Euclidean features, we use polar features. So it nicely illustrates the power of feature engineering. Another thing that we can do with, in case of lack of predictive power, is use Bayesian networks. And in my PhD, I already studied Bayesian networks. I did my PhD in 2001. In 2003, sorry, in 2003, it was in 2003. Almost forgot. You can download my PhD from my website, dataminingapps.com, if interested. And in there, I already studied Bayesian networks because I was fascinated by it, because it allows to very easily combine domain knowledge, business knowledge, with data knowledge. And when you're facing a lack of predictive power, that unique mix of domain knowledge and data knowledge can come in very handy to boost the performance of your analytical model. And that's exactly the very strength of Bayesian networks. It allows us to model a joint probability distribution over a set of categorical variables using either patterns that we learn from data or patterns that we learn from domain experts. A domain expert is like a credit expert, fraud expert, marketeer, etc. And a Bayesian network has two parts. It has a graph, G. It's a directed acyclic graph, which has nodes, and the nodes could represent variables. In a moment, we'll give an example of that. The variable could be like income, could be employment status, could be marital status, could be savings account status, etc. And the edges indicate conditional dependencies, like the amount on my savings account is probably dependent upon my income. So I have an incoming arrow from the node income to savings amount, because savings amount is dependent upon my income. The arrows or edges will specify conditional dependencies and conditional independencies, and then the strength of those conditional dependencies will be specified using conditional probability tables. We'll see an example of that in a moment. And because Bayesian networks are so intuitive, they're often referred to as probabilistic white box models. Instead of a deep learning model, which is often referred to as a very complex black box model, here we have a probabilistic white box model because it clearly shows us the variables as well as the dependencies in between. So a Bayesian network consists of a directed acyclic graph. So directed means that there's arrows which are directed. It's acyclic. It cannot contain cycles. It has nodes, which are typically variables, and edges, which represent connections. Theta is then the conditional probability distribution. So here you can see, let me quickly show an example. This is an example of a Bayesian network. Here I have various types of nodes: income, deposit, payment, housing, and security. And actually the arrows indicate dependencies, like security depends upon housing, payment depends upon income, and payment depends upon deposit, and deposit, or let's say savings amount, depends upon income. So the nodes represent my dataset variables, and then the arrows indicate the dependencies. This is actually a Bayesian network which I took from a paper already in 2004, so it's about 20 years old, but I think it's very relevant still nowadays, because the Bayesian network does not only have the graphical representation, it also has these probabilities, right? So A doesn't have any incoming arrows, so that means we can just look at how many people have high income, how many have low income. You can just look that up in your data set. 30% have high income, 70% have low income. Then I can look at deposit. Deposit, well, whether I have small or large deposit, depends upon the income, right? So if I have high income, A, the probability I have large deposit is 0.1. If I have high income, the probability that I have small deposit is 0.9. If I have low income, probability I have large deposit is 0.6. Here for payment, you can see that we have two categories, default, which is C, and not C, which is payback. So C depends upon A and B. So if I have high income, A, small deposit, not B, probability that I will default is 0.5, and probability that I will pay back is also 0.5. That's how you should read those probability tables, right? And now I go back a few slides. So those probability tables are actually this big theta. So it contains the probability of like payments given the parents of the payment variable. The parents of the payment variable in my figure were income and deposit. So the conditional probability of paying back or being a defaulter depend upon the values of the direct parents as reflected in the Bayesian network. And we have that for every value of the variables. In other words, we can clearly see the dependencies between all the network variables such that the network nicely models a joint probability distribution of each of the variables. What's the combination? What's the probability of the combination of values appearing? Well, that's the exact multiplication of the corresponding probabilities, whereby we multiply the probability of every value occurring, payback or default, given the parents that we observe, right? Given whether income is high or low or deposit is small or large. So the joint probability nicely factors into this product of probabilities according to the structure of the Bayesian network. Now, how do you get Bayesian networks out of data? Well, you get Bayesian networks out of data using two steps. First step is you learn the structure of the network graph, right? And the second step is you learn the probabilities. And the probabilities are usually the empirical frequencies, right? So if I have to learn these probabilities, knowing that the graph is already there, you just count how many customers have high income, how many have low income, how many have, for the ones that have high income, right? How many have large deposit, how many have small deposits. So you just count in your data set those probabilities. You just count the empirical frequencies and then you represent them as the probabilities, a method which is sometimes also referred to by statisticians as the maximum likelihood estimation. Okay, so in the data, the way the structure is being can be learned is we can either learn that from data directly, and there exist methods in the literature that allow us to do so. Correlational based methods based upon all kinds of fancy correlation measures, amongst which also mutual information, for example. Or I can also resort on domain experts, marketeers, fraud investigators, credit decision makers, etc., that will help us draft a Bayesian network. And once we have the Bayesian network drafted, we can then combine that with the data that we have available in order to get those probabilities. So Bayesian networks are a very nice mechanism to combine knowledge from domain experts enriched with knowledge from data. So if you're going for the domain expert approach, I can look at, for example, I can interview credit experts or fraud investigators, and I could ask the fraud investigator, what are the important variables to decide upon whether a car insurance claim is fraudulent, yes or no. And he or she then lists the variables, like maybe the type of car is important, maybe the color of the car is important, maybe the type of damage is important. So all the variables are listed, and once all the variables have been listed, you can ask the domain expert to then draw dependencies. Is there a variable that depends upon another variable, you think, based upon your experience? And very likely, if you would interview 10 experts, you're not always going to have the same answer. So you can have knowledge conflicts, with one expert saying that there's a dependency there, the other expert ignoring this and saying this is not true, there's no dependency there. So that's something that you have to deal with. See, like when there are knowledge conflicts. But obviously, if you have like 10 experts and 8 state that there's a dependency, 2 state that there's no dependency between 2 nodes or 2 variables, then you can go with the majority vote and assume there is a dependence, right? And then once you have drafted this Bayesian network from data, you can estimate the probabilities by looking up the empirical frequencies in the empirical data, and then you can do reasoning, because once you have this Bayesian network, you can use it to predict anything. You can use it to predict any variable of interest given values for the other variables, even when some of the other variables are missing. That's one of the nice traits of Bayesian network analysis, is that you can very easily reason with missing values, because you can we call that in statistics, or in Bayesian statistics, marginalize over variables. Let's have a quick look at how we can use a Bayesian network to reason. Assume that we have a customer that applies for credit, and he or she has high income, so that was A in my previous plot. Small deposit, not B. No security, not D. And he or she has real estate property, so E. So from the network, I can now compute that joint probability of all those variables occurring. You see? So actually what I'm doing here, I'm just applying this formula that I have right here. I factor the joint probability according to the conditional probability as witnessed in the plot. And that gives me this joint probability right here. What I can then do is, because what I'm after, I want to know whether this person is credit worthy, yes or no. So my C, the payments, whether it's default or payback, that's what I'm after. So basically what I will be doing then is I will also calculate the joint probability of not C together with all the variables as I've observed them. And that gives me this. Obviously, I'm interested in the conditional probabilities. I want to know, given that a customer has small income, given that a customer has high income, small deposit, no security, and has real estate probability, and has real estate property, what's the probability that he or she is going to default or non-default? And applying Bayes' rule, I can just normalize then these two probabilities by dividing by their sum, and you can see that the probability that he or she will be C, and C is indeed default, is about 80%, and then the probability of not defaulting is obviously the complement thereof is about 20%. And applying the winner takes all rule, which we always typically apply if we're doing machine learning and if we're working with outcome probabilities, we would go for default or class C. So that's how Bayesian networks work. So they allow us to very easily reason with data and dependencies. Specification risk is also a type of risk which is discussed in our book, and it actually has a separate chapter. I only highlight some of the things, but specification risk, one example is incorrect target definition, right? Oftentimes your targets are not perfectly defined. Like if you talk about customer lifetime value, ideally you should consider the entire lifetime of a customer. But for mortgages, this could be 20, 25, 30 years, right? And we cannot predict that far in the future. It's simply impossible. Oftentimes, for CLV, for example, we adopt a 2 or 3 year time horizon. So the T is already not perfect, but it's because we cannot predict that far in the future. Also, when you look at the revenues and the costs, should we consider direct revenues or also indirect revenues? If a customer gives you revenue and he or she is really happy with your product or service and also gives you positive feedback on Twitter, on Facebook, or on Instagram, or maybe positive word of mouth, then obviously this should also be factored in to the revenue. It's an indirect revenue. Same goes with the costs. What are the costs of initializing, maintaining the customer relationship? Same goes with the discount factor. What discount factor should we adopt? Usually this will be the weighted average cost of capital, the WACC, right, which is like the cost of equity and cost of debt combined according to both proportions. But you see that there's a lot of issues that come with operationalizing the CLV target value, which makes it not always perfect. Same goes in fraud detection. If we look at fraud detection from a supervised setting and we look at a set of historical fraud claims or a set of historical claims, some of which are fraudulent, some of which are non-fraudulent, well, the labeling fraudulent or non-fraudulent has typically been done by a fraud investigator. And oftentimes, this fraud investigator has a high suspicion that a claim is fraudulent, but is never 100% sure about it. So the labels that we see in supervised or predictive fraud analytics are often based upon suspicions rather than being fraud per se. So there also we have incorrect target definition. Probably we're very close to it, but it will never be perfect. If you look in credit risk modeling, if you look at the Basel Accords and IFRS 9, typically we tackle credit risk modeling using a definition of defaulter, which is being 90 days in payment arrears, yes or no. But sometimes, I mean, people can recover after being 90 days in payment arrears. So alternatively, instead of fixing on that 90 days threshold, we could also just predict the raw amount of number of days in payment arrears. Or I can also look at the time of default, etc. And the same goes actually in credit risk modeling. It's not on my slide, but also for LGD, loss given default. Loss given default is the percentage of the exposure that a financial institution or lender is likely to lose upon default of a customer. There's also lots of things that pop up there, like what cost should we include, what discount factor, what time horizon, which kind of complicates the target definition. In case you're interested in knowing more about good target definitions for credit risk modeling, I'm happy to refer you to my paper boosting credit risk models, which you see mentioned at the bottom right there, and which was written together with a colleague, Professor Christine Smets, and recently, a few months ago, accepted in the British Accounting Review. Specification risk also relates to uplift modeling, right? Uplift modeling means that you carefully think about your customer population, about who to target. You still remember when you're doing uplift modeling, we have various types of customers, right? We have customers that we have like lost causes, right? The ones that we shouldn't target because they're essentially lost causes, so we should not target them. No matter what we do, they're a lost cause. We have the sure things. These are the ones that will react to your marketing campaign anyway. So actually, these are the ones that will react anyway. They don't need a marketing campaign in order to be convinced to do something. We have the persuadables. These are the ones that actually need the marketing incentive, whether it's a retention incentive or whether it's an offer you're making or whether it's a response campaign that you're doing. The persuadables are the ones that need the marketing action in order to be persuaded. And that's the one that we want to target. And then we have the do not disturbs, the ones that don't want to be disturbed, because if you disturb them, it's going to create an adverse reaction. So actually, when you're doing response modeling or churn prediction and you're planning on doing a marketing campaign in order to get some marketing response or prevent customers from churning, you want to make sure that we have the persuadables, the ones that need the marketing incentive in order to respond, or the ones that need the marketing incentive in order to not churn or stay. So we have to carefully think about our development sample, on which we have a control group and a treatment group. The control group, which is not subject to any marketing action, and the treatment group, which is then subject to the marketing action, which is being treated by a marketing action that could be a flyer, a brochure, a banner, etc. And then you can make a churn model on both the control group to see which are the ones that spontaneously churn and which are the ones that churn after having received the treatment. That's the churn model on the treatment group, and the difference can then give you an uplift model. So this all relates to specification risk, to how you're going to specify your target definition. And there exist some very exciting techniques that allow you to do so, like the approach by Victor and Lowe, where you actually use a logistic regression model in order to develop this type of uplift modeling. Multicollinearity is also something that I hear a lot. I get a lot of questions on multicollinearity. Multicollinearity in any type of regression model is an issue. It's typically always there. You will see multicollinearity between age and income, sometimes between income and savings amount, sometimes between age and number of years clients or time on books, etc. So it's always there. But multicollinearity means that two variables measure the same thing, and if it's not perfect, the multicollinearity, so if the correlation is not 100%, it means that they're measuring to some degree the same thing, but not exactly 100%. So there's still a difference to what they're measuring if the correlation is not 100%. And the thing is, if that correlation is not 100%, maybe the difference in what they're measuring is relevant for your target. yet you still have multicollinearity in your model. And the effect of having multicollinearity in any type of regression model is that your standard errors become pretty wide, they become inflated, so that gives you very wide confidence intervals and very inflated p-values. The regression coefficients will be very unstable because of the multicollinearity, right? Because part of the predictive power is gained from another variable, and actually the predictive power is spread out across multiple correlated variables. Instead of one variable consuming all the predictive power, is now spread out across multiple variables, which kind of makes the confidence intervals wide and gives us inflated p-values. So the regression coefficients can be highly unstable and dependent upon the predictors. It will also complicate the interpretation because part of the interpretation is now spread across multiple variables, which also complicates things. My take on multicollinearity is that obviously when there's perfect collinearity, then you should remove variables from the data because they're redundant. But I always evaluate it in a profit-driven way, in a performance-driven way. I always look at the things that really matter, which are, for example, area under the ROC curve, R squared, Gini coefficient, or maybe you look just like at profit-related measures, some of which we have developed in my group. And if the presence of multicollinearity is justified because it nicely adds to the AUC, to the R squared, or to the profit, then that's perfectly fine with me. At the end of the day, you want to predict, you want to discriminate defaulters from non-defaulters, fraudsters from non-fraudsters, and if there's some multicollinearity that is needed in your model to appropriately do so, then as a non-hardcore statistician, I am perfectly cool with this. So that's my take on it. Development risk is also something that is very important. Development risk is actually the type of risk that you encounter as you start developing models. Again, in the book, we have various types of development risk that we discuss. We discuss domain knowledge paradox, citizen data scientist risk, data leakage, assumptions, model isolation, documentation. Here I'm just going to highlight a few of them. Citizen data scientist is a very important development risk because it has become so easy to develop models, analytical models, that even people having almost zero knowledge of analytical models or of machine learning can develop an analytical model. Just by calling a few routines, or even when you're working with a graphical user interface based tool, clicking a few buttons, you can develop an analytical model. The biggest danger is there that you're developing a model and you don't know what you're doing. You cannot imagine the number of times I've seen amongst my students or in industry random forests being used to do churn prediction, to do fraud detection, credit scoring, etc., without the modeler, the data scientist, knowing what a random forest is. If you see a random forest being used, ask the person, the data scientist, what a random forest is. If he or she cannot clarify what a random forest is and where the name random stands for in random forest and why it's not giving me random performance, then I don't trust the models, right? So the citizen data scientist risk is a very important risk because sometimes people develop models without properly knowing what they're doing. Another type of risk, and I've seen this risk popping up a lot, is data leakage. When you develop models, there should always be a very clear separation, a Chinese wall, between your training set, also called your model development sample, and your test set, which is also called your holdout sample. Your training set is used to do the full model development, right? Starting from pre-processing to the final model and model evaluation. Your test set gives you an independent performance assessment. You can never touch upon your test set during model development because if you do so, you have data leakage. You can have actually two types of leakage. You can have feature leakage. Feature leakage means that you have part of your training, part of your predictors actually are too much related to the target in an unfair way, right? Part of your, let's say you're doing credit scoring and then you're predicting whether a customer is going to default yes or no, and one of your predictors is time of default. Then obviously for all the defaulters, time of default will have a date, and for the non-defaulters it will not have a date in there. So that's feature leakage. Your feature is telling you something about your target in an unfair way, which is not supposed to be the case if you would start using the models for real. If you would start using the models in production, you cannot ask for the time of default of your customers, right? Because they still need to have the opportunity to default yes or no. So you have your feature that tells you too much about your target in an unfair way. That's what we call feature leakage. You can also have instance leakage. Instance leakage means that you can have instance leakage in various ways. Sometimes some data scientists, some modelers, they start from an entire data set. They do the missing value handling on the entire data set. They look at missing values. They impute them with the median or with the mean. They detect outliers using box plots. They detect outliers using z-scores, and they treat the outliers on the entire data set. After they've done that, they split the data set into a training and a test set. That's unfair. That's data leakage because you have used observations of your test set to calculate the mean or median to impute the missing values. You have used information of your test set to help you detect and handle the outliers. That's just wrong. That's data leakage. Your test set should always stay untouched. So you first do your data split, and then you do all your modeling on your training set before you start assessing the performance on the test set. Data leakage or instance leakage can also occur because of oversampling. When you're having a skewed class distribution, for example, with only a few fraudsters or a few defaulters, and you did oversampling, you duplicated it, and then afterwards you split into a training and test sample, it may well be that some of the duplicated fraudsters or defaulters end up in your test sample. So you have seen them before, which is not a very nice thing, right? So that's also something that you should be aware of as you're starting to do your data pre-processing, especially with oversampling, for example, in this case. Your training set and test set should always be strictly separated. Also, when you develop models, typically you make assumptions, right? In linear regression, once we start doing the statistical inferencing, etc., oftentimes we make normality assumptions. We assume that observations are independent, that the data is IID, independent and identically distributed, etc. Well, oftentimes these assumptions are simply not fulfilled or not 100% fulfilled, and yet we have to do something with the data. Many times these assumptions will not be there, so people start sometimes doing logarithmic transformations to make the data look like a bit more normal, or sometimes they do PCA, which stands for Principal Component Analysis. If you want to work with perfectly uncorrelated predictors, then you can work with the principal components. Principal component analysis is a way to transform a set of predictors into a set of uncorrelated, literally with zero correlation in between principal components. But the thing is, if you do this on a real life data set, is that oftentimes these principal components are very hard to interpret. In textbooks, where you see textbooks examples of principal components, they're always nice to interpret and it works out nicely. In real life, if you start doing principal component analysis and use the principal components in your logistic regression or in other types of analytical models, then you end up with a black box model anyway, because the principal components are just linear combinations of your existing variables and as such black box elements. My idea here is, or my take on this is, always go for a pragmatic approach and focus on performance, whether it's AUC, whether it's R squared, or whether you're into profit. That's what you should be your goal. At the end of the day, even if some of these assumptions are slightly violated, as long as you come up with a meaningful predictive model in terms of AUC, profit, etc., you're doing fine. Also in developmental risk is model isolation. Oftentimes, if you look at many modern day companies, you see that models are being developed as stovepipe applications. So you have risk models that are being used in the marketing department, risk models that are being used in the trading department, risk models that are being used in the fraud detection department, in the credit department, etc. So you have analytical models that are being used for credit risk, for market risk, for operational risk, for marketing risk. And oftentimes you see that these models are being developed rather asynchronously. So there's no company-wide standards for uniform data definitions, uniform pre-processing routines, like the way you treat missing values, like the way you treat outliers, etc., like the way you document your models, etc. So this model isolation can get can become quite an issue as you start to aggregate risk measurements that come out of analytical models across various departments into one overall risk measure. Do note that there have been some statistical techniques based upon copulas, for example, that allow you to jointly combine different types of risk measures as long as you know some of the dependencies or correlations between them. But still, I mean, from a pragmatic or consistency perspective, model isolation is a very important problem firms are exposed to nowadays. Technological myopia is another one. Oftentimes we see if there's a new evolution, if there's a new technological innovation, like NoSQL databases, like deep learning, many firms are being tempted to jump too quickly on that bandwagon. Always be skeptical when you see new developments, and always have technology mature a bit before you start using it, because oftentimes it can create a lot of investment and create problems down the road. Deep learning, for example, is a technique which you should be very careful when you use it. Like on tabular data for churn prediction, for fraud detection, for classical credit scoring, you will not see any benefit of deep learning methods. We tried that quite extensively in our research. But on unstructured data like images, like audio, like video, you will see a lot of benefit from deep learning. Convolutional networks are really good in processing imagery. Transformers are very good at processing text, etc. So anyway, the point I want to give is don't be blinded too quickly by some technological innovations, because it may cost you a lot of money at the end of the day without having any benefit. Also, when you develop your models, there's the risk of programming errors in Python or any type of software. There's the risk of syntax errors. Those are easy to detect because you will just get an error from your software environment and you can start debugging. But there's also semantical errors, which are more related to the reasoning of your analytical script, and those are much harder to detect. That's why software programs or analytical programs should always be properly checked before they are being put into deployment. And then comes the big question, like, should we go for open source software like Python, which is very popular, R, or commercial software like SAS, MATLAB, etc. Both have their pros and cons. Open source is for free, but you do not always have a quality guarantee. Everybody could contribute to open source software, and you do not always know is it trustworthy, yes or not, especially if you're working on very specific topics. Commercial software has the disadvantage that it's not for free, but modern day commercial software is more centered around solutions end to end, right? End to end. So it starts with the data collection to the fraud detection to the case management, case handling, follow-up, etc. It's an integrated solution it provides that has been quality proven and that has been thoroughly tested by the development teams of the commercial software vendors. So both of them have to be clearly contrasted, especially in terms of total cost of ownership, before deciding which one you're going to go for. Validation risk. In the book, again, we have various types of validation risk that we refer to, like test set torturing, incorrect cross-validation, unexpected signs, etc. We're going to do some of them, like unexpected signs. Sometimes you can have variables that have an unexpected sign that come out of your linear or logistic regression model. Let's say that your logistic regression model tells you that for your data set, the more debt a person has, the more likely he or she is to be a good payer, or the better the creditworthiness. It's an unexpected sign. Those unexpected signs can originate from various sources. They can originate from multicollinearity concerns, because you have multicollinearity, you have inflated standard errors, which because the standard error got inflated, it also could create an unexpected wrong sign. So it could be due to multicollinearity, sometimes poor data quality, because the data element is not measuring what it's supposed to measure. It's not measuring depth, or it's measuring that in the wrong way, for example. Or you have non-monotonic behavior and a biased sample. You can see a drawing that I borrowed from one of my big mentors in credit risk modeling, which is Professor Lynn Thomas. And he found on a data set that the default risk, and here you can see like a measure of default risk, like percentage of defaulters or an odds ratio. And the higher risk, the higher the value on the y-axis, the more risky. And here you can see the pattern with age. So you can see a general declining pattern, which is quite obvious. The older you get, the less risky you get. But you can see a small bump, right, from 26 onwards. I don't know what's the reason why you get more risky from 26 onwards. Maybe, I don't know, marriage. Anyway, I don't know whether that's risky or not. I leave that up to you to decide. But here, from 26 onwards, you see that the risk increases. And that's a pattern that has been observed in certain real-life data sets. Well, imagine now that you have a biased sample of only 26 to, let's say, 35 years old. If you only have a sample of these guys, then obviously you will see that higher age leads to higher risk because you're not covering the entire spectrum. Because of this biased sample, you have like a biased view on the impact of your predictor, or in other words, you have an unexpected sign. So when you have an unexpected sign, you always have to diagnose what could be the reason behind this. Wrong evaluation metrics is another type of validation risk in the sense that oftentimes you see analytical models evaluated in terms of statistical performance. Like people are going to look at area under the ROC curve, lift curve, R squared, mean squared error, mean absolute deviation, Pearson correlation, etc. Excuse me, I have a bit of a cold. So this is good, but we can also take it one step further and really start looking at the bottom line impact. And the bottom line impact for any commercial firm is profit. So in my research group, together with some very bright PhD students, we developed profit measures for churn, but also for credit scoring. And once we've developed those profit measures, we use them to build models. And we have ProfTree, which is profit-based decision trees. That was built, or that was suggested in this first paper with Sebastian Hübner and Eugen Strüppling, and Seppe van den Broeke and Tim van Verdonk. These is an extension of decision trees whereby we build decision trees that are not minimizing the impurity, but are directly optimizing profit. We did the same for logistic regression and developed ProfLogit together with Eugen Strüppling, Seppe van den Broeke, Katrien Antonio, myself, and my colleague Monique Snoek. We developed ProfLogit, which is an extension of logistic regression, where we directly optimize the logistic regression coefficients. We use logistic regression because that's interpretable using a genetic algorithm so as to optimize the expected maximum profit. You can find publicly available software implementations of both of these techniques on GitHub if you just Google the papers or the paper titles. Validation risk is also about model auditing. Given the strategic impact of analytical models, which is now bigger than ever before, they should be audited, properly audited, right? And here you can see some international standards organizations or ISO 2018 guidelines for auditing management systems. Auditing should always rely on integrity, based upon a fair presentation, based upon due professional care, based upon confidentiality, based upon independence between the audit team and the entity that is being audited. It should be evidence-based, and it should also factor in any types of accompanying risks. Now, if you're organizing this as a company, you can organize this internally or externally. Internally, there's two options that you can go for. A Chinese wall principle. Chinese wall means that you have the development team, the model developers, the data scientists that develop the analytical models, and you have the model validators or the model auditors that audit or validate the models developed by the development team. And there's a Chinese wall in between. There's a strict separation in between. I've seen this being done in a few American firms that I've collaborated with, and I can tell you, sometimes it created a lot of friction between both teams because no team likes to be watched upon too closely by another team. So in order to get rid of that friction and that kind of destructive collaboration that I've witnessed in certain types of firms, they used rotational employment. That means that people shifted job roles between development and validation teams depending upon the type of project. And that, if you organize it internally, I think is a better approach to do internal validation. You can also do it externally, which means that you have an auditor that is going to externally validate your models, but you kind of have an agency problem right there, because obviously when you're an external consultant and you're validating an analytical model and you're being paid for that, sometimes you don't want to be too harsh. You're focused on making sure that you establish a long-lasting relationship. So as a firm, deciding upon whether you're going to do the validation externally is something that you also have to look at the total cost of ownership or the total cost of the partnership there, knowing that the external partner is actually his or her primary focus is to develop a long-lasting relationship with you. So that's something that you should properly consider. Operational risk. Well, risk is the type of risk once the analytical models are starting to be put in operations. We have data drift, which are changes to features, right? Changes to the data elements that serve as predictors in your model. We can monitor that very easily using descriptive statistics. You look at the mean age, the median age, the variance of age, the minimum of age, the maximum of age, the confidence interval of age or of income, and you look at whether the values that you get on your training sample are very similar to the values that you get on the newer sample, the newer type of customers that you're scoring, right? You can also look at whether missing values in your training sample and correlations between variables, whether they remain constant in the newer data that you're observing, or whether there's shifts in there, whether there's data drift. That pretty much relates to your predictors. Output drift relates to your predictions. How many people on average do we predict as fraudulent, as defaulter? What's the average CLV that we predict? And that we can then contrast to what we predicted on our training sample and see whether there's trends in there. That's output drift. You can very easily diagnose output drift using a system stability index or Kullback-Leibler divergence metric, right? Which allows you to see whether you have output drift, yes or no. Target drift then doesn't look at predictions, but it looks at the true targets. To what extent, if I look at my true targets, do I see more fraud, more defaulters? Do I really see more customer lifetime value or less, etc.? To what extent do I see target drift? Usage drift then relates to how much the model is being used. Is it being more used or is it being less used? If you see that the model is being less and less used because there are more and more model overrides, which means that a human expert overrides the model's predictions, then it indicates that people are trusting the model less, and it's a kind of sign of distrust, which means that you're running into a serious operational risk issue there because models are being less used, people trust them less, etc. Brings us with security risk. Security risk is analytical models are more and more also subject to security risk, especially in fraud detection. Fraudsters try to continuously outsmart your models. They try to continuously find for the weaknesses, the loopholes in your analytical models, such that they can conduct their fraudulent activities. They're going to try and do some phishing, try to get information in a malicious way by pretending that there's some kind of legitimate identity. Maybe they will use deepfake, right? So there was once this story of somebody that deepfaked the voice of a CFO, Chief Financial Officer, in order to make the CEO of a company do a money transfer. So the fraudster using deepfake technologies, and deepfake technology is the usage of deep learning to generate fake images, to generate fake audio or fake videos. So by using a deepfake audio, I can start learning somebody's voice, and I can start calling somebody pretending that I'm somebody else. So if I could learn the voice of a CFO of a company, and then I could call the CEO and make him do a money transfer, a fraudulent money transfer on my bank account. It happened once, I think, to a Swiss firm, and it's getting more and more of a problem nowadays. You could also outsmart models in another way. Many firms in their churn prediction models look at the interactions with the customer service desk. If I have lots of interactions with the customer service desk, it indicates that I'm most likely dissatisfied and I'm at risk of churning. So what I could now do, I could say, hey, I'm actually happy with my telco provider. I'll just do a few calls to my telco provider to say that I'm not happy, because what will happen next is that they will probably want to retain me and they may do me a more favorable offer. So I'm doing just fake customer dissatisfaction calls. I'm just complaining for minor things which really I'm not bothered with, just to get that better offer, just to make sure that they give me a better offer. Fake customer dissatisfaction. Credit application fraud. If I want to apply for credit and I have to file a credit file, a credit form. I have to fill in all kinds of details. Suppose I'm unemployed, but I'm indicating that I'm employed. I actually fake my income, etc. So credit application fraud is another way to outsmart models to make sure that your credit application gets accepted. Model backdooring is the technique whereby a nefarious data scientist or a fraudulent data scientist builds in a model backdoor for carefully crafted input, such that the data scientist knows that once the model is put into production, he or she can, using a unique combination of input values, of values for age, of values for income, savings amount, etc., using a unique combination of input values, he or she knows that the model is going to give a favorable outcome. Credit accepted, transaction non-fraudulent. That's model backdooring. You build a backdoor into the model to make sure that for a specific combination of inputs, it performs exactly the type of activity that you want it to perform, which is very easy with highly parameterized models. If you have models that are highly parameterized, like deep learning neural networks, you can very easily build in those backdoors in order to make models behave the way you want them behave. Or also through data poisoning, whereby deliberately you inject poisonous, fraudulent, incorrect data into the model such that the model learns this incorrect data and the patterns that are in there in order to make it do the behavior that you want it to do. That's model backdooring. Then we have model exfiltration. Well, many modern day analytical models are being deployed or exposed through a public API, application programming interface endpoint. That's like you can just call an analytical model and look at the outcome. Some researchers have done research on how you can repeatedly query a model through its API, which is public, and so as to steal the model, know how it works, and exfiltrate it. So if a model is being exposed through an API, I can repeatedly call it using special set of inputs and then learn another type of model, which in essence is very much the same as the original analytical model. What actually happened then is that I exfiltrated the model. I extracted it, I stole it. That's model theft. And that just like we have denial of service attacks, which is an attack that you often see in networks and in the internet, whereby servers are being overloaded with requests so as to have them crash or go down, you can also have a denial of prediction attack. Make sure that the analytical model crashes. I could do that by overloading the API endpoint with requests, right? Or I can spam the analytical model. I can submit data to make it crash, to make it do a division by zero, right? If I know that the analytical model uses some kind of accounting ratio, I can try and see what happens if it's being exposed to a division by zero. If I give it missing data, if I give it unseen categorical variables, let's say that marital status has 4 different values, and I give it a fifth value, how it's going to react to that. I can try and overflow the GPU memory allocation and so on. All of these will cause a denial of prediction attack. Finally, to conclude, there's managerial risk. Again, in the book, we have plenty of stuff to say about managerial risk. Transition risk, how you transition to your old model. Maybe it's an expert-based if-then model, or maybe an old analytical model trained using logistic regression, to a new model trained using deep learning, for example. In order to make these transitions smooth, some firms will adopt a migration period, during which they combine the old model with the new model in a weighted way. So they can adopt, in credit scoring, they typically adopt a 6-month transition period, and gradually during that 6-month transition period, less weight is being put on the old model and more weight is being put on the new model. Model governance is also very important. Senior management and executive directors should be aware of all the efforts that are taking place in the analytical arena in their firm. They should show active involvement, assign clear responsibilities, make sure the procedures are in there to fully thrive on analytics. They should be actively involved during the development. They should know what's going on there, but also during the validation and also during the deployment. They should know how the analytical models steer and actually constitute the backbone of their strategic decision-making processes. That's really very important. And oftentimes we see things like waste of analytics. We see like very good analytical models that have been developed by a very skillful analytical team, but don't end up being used because there was no trust, because there was no good model governance in place, because there was no active involvement of senior management, and because they were not involved from the outset of the analytical project. Once the models got delivered, they got very skeptical because those models were very complex mathematically, etc., and they didn't want to use it. And that resulted into a waste of sometimes even very sophisticated, beautiful analytical models. Regulation risk is also very important, right? Like GDPR, Global Data Protection Regulation, is something that's very important in the EU to know what data you can use when, where we also have things like the right to be forgotten. So every entity has the right to be forgotten and have his or her data erased by any type of company. Now we have the EU AI Act, that is also giving us clear guidelines about the development, but also the usage of AI models. Model ethics is also very important. There's more and more data that can be used for various types of purposes, but what data can we use for what purpose? Can we use call detail record data for credit scoring? In previous research, together with an ex-PhD student, we collaborated with a South American firm and showed that call detail record data is predictive for your credit worthiness. At first, this may sound like very privacy intrusive, but sometimes what seems as a risk can also be something that is very advantageous. Like, for example, in developing countries where people don't have historical credit data. For minorities, for which banks do not have historical data available. Sometimes using their phone data, obviously with their permission, could actually help them get access to credit. So what could seems as a privacy hazard at first could also present an opportunity. But yet, it's an important aspect of model ethics. Can I use social media data for credit scoring? Another ex-PhD student of mine, David Martens, did research on using Facebook data for credit scoring, and found that the pages you like and the pages your friend like are very useful information for credit scoring. But obviously the question is, can we use that? Right? To what extent, what data can be used for credit scoring? And it's not because it's publicly available that you can just use it like this, right? What about latent discrimination in credit scoring? What if you don't have gender in there because you're not allowed to discriminate based upon gender, age, ethnic origin, or beliefs in your credit scoring models? But what if you have variables that are not measuring gender as such, but are correlated to gender? Maybe, unfortunately, in some countries, income is still correlated to gender. So what if other variables are correlated to sensitive variables like gender, like belief, like ethnicity, etc.? How are you going to take into account these correlations, which actually give you latent discrimination? It's another example of managerial risk. Finally, I have climate and ecological risk, which is also very important, especially if you look at the deep learning models that are being used nowadays, the large language models like ChatGPT, BART, and Llama, Meta's Llama. Those models are typically built using billions of parameters, as such leaving behind a very heavy carbon footprint in terms of CO2 emission. According to some unverified information, just a guesstimate, we know it's a lot, but based upon that URL that you see right there, GPT-4, which is the most recent version of OpenAI's GPT, emitted more than 15 tons of CO2. So given that those LLMs will be more and more being used in industry, it's also important to be aware of their ecological footprint. Climate risk and ecological risk will also be very important for measuring credit risk, because one of the key variables in credit risk is loss given default, the default that will occur upon a loss, the loss that will occur upon a default. And one of the key variables to predict LGD is the loan-to-value ratio, the value of the remaining exposure to the value of the collateral. Values of collateral that are highly affected in flood-risky areas. So given that flood risk is probably on the rise, then obviously this will affect LTV, loan-to-value ratios, and as such LGD as well. Given weather forecasting models that become more and more important, especially if you want to do smart irrigation. I have a research project where we do smart irrigation using Internet of Things technology, where we intelligently put sensors, IoT sensors, in pear and orange orchards that measure the soil moisture in order to predict when we have to irrigate, right? So smart irrigation, making sure we don't waste needless water, etc., nor electricity, is also becoming something very important given climate change and the accompanying ecological risk. Obviously, this also brings about new ways of doing fraud. Whenever there's something new, there's always some fraudsters that jump on it as well, which is greenwashing. Greenwashing means that companies might be tempted towards offering products that contribute to a better ecological environment and help reduce climate risk, but actually the services and products as such are not doing it. They're just using the climate change or green agenda as an argument to help sell their products or services in a fraudulent way, which is obviously not nice. Conclusion: you see that model risk, as we wrote it down in this book, it encompasses the entire realm of analytical modeling, right? So it starts from data risk, then specification risk, development risk, validation risk, operational risk, security risk, and managerial risk. So there's a lot of risk that comes with it. And what's really very important as you start to deploy your analytical models in industry is to qualify your model risk as good as possible, be aware of it, and sometimes you cannot remedy it. Sometimes you can remedy it if there's bias and you can circumvent it, you should do that. Sometimes you cannot, but then it's very important to document it, to be aware of it as you start making your strategic decisions, to be aware of the fact that no analytical model is perfect, but being aware of its shortcomings is very important um, um, in order to strategically use it in the best possible way. Remember the quote that I mentioned earlier, made by George Box: all models are wrong, but some are useful, right? Okay, if you want more information, I'm happy to refer to this book, as I said, which you can get on Amazon.